Hello everyone, welcome back to this YouTube channel. So in this video, we are going to talk about time in distributed systems. So I think it's easier to explain this with a real example, okay? So let's say we have a Facebook group where we can have some posts and also people can post comments on a specific post, okay? So let's say now we have a user who have a post which says, what car do you guys own, okay? And do you like it? And the first user replies, oh, I have Tesla Model X. I owned it 3 years and never regret it. And the second user saw the message from the first user. And then he also posted a comment. Oh, you own Model X? Birds of a feather flock together, okay? It's an interesting reply, okay? Anyway, so here we show the first comment first and then the second comment, which is correct, right? So, and let's see both users comment when they post the comment, they hit the same server, right? They hit the same virtual machine or the same physical machine, okay? So let's say we use a timestamp for each comment. So this timestamp is, let's say 9 o'clock and 31 seconds, okay? AM, okay? And this one shows, oh, this is actually from 33 seconds, okay? AM, okay? So because both comments hit the same machine, so it will have the exact same time, right? So I mean, the time given by this machine is very determined, right? So for example, for the first comment, it says it's commented on 9:31, and the second comment it says it's commented on 9:33. Both of this time are from the same machine, right? So from the time we can definitely tell, okay, this is the first comment and this is the second comment, and then we show them sequentially in the feed, okay, which is correct. Now let's see a different case, which is, oh, these two comments, when the user comment the two comments, okay, so they hit two different machines. So let's say the first comment hit machine 1 and the second comment achieves on machine 2, okay? So let's say both machines have exact same time, right? So when machine 1 is 9:30 o'clock, then machine 2 is also 9:30 o'clock. So their clocks are exactly the same. Then we have no issue, right? Because for the first comment, we still show 9:31, and for the second comment, it still shows 9:33 second, okay? And we still show the comments in the correct order based on the time, right? So now, in reality, actually different machines, because they have different clocks, they have different hardwares, right? It's impossible for them to have the exact same clock. So for example, at the same time, maybe on machine 1, it shows 9:31, but on machine 2, it shows 9:35, right? So they have different time, even though it's at the same time, right? So in that case, there will be some problems in our example, okay? So let's say the first user, he commented the post, right? And let's say the comment hit machine 1, okay? And machine 1's time is still 9:31, which is no problem, okay? But for the second user's comment, it hits machine 2, and machine 2's time is actually 9:28, okay? Cool. And now, when we show the comments for this post to the users, okay? Because this time is before this time, right? So actually now we will show the second post, or we will show the second comment first, before the first comment, right? So now what you see is, you will first see this comment, oh, you own Model X, birds of a feather flock together. And then you see this comment, which is Tesla Model X owned 3 years and never regret it. This is strange, right? Because the second comment should be behind this comment, right? Because this comment, the user sees the Tesla Model X comment first and then replied to, and then created a new comment based on that, right? So in this case, you can see the orders of the messages we show in the feed is wrong because of the different times on different machines, right? Okay, so this is a problem with time in distributed systems, okay? So how we can resolve this, right? So how we can see, okay, even the time on different machines are different, but we can still guarantee the order of the data is correct. Okay, how do we do this? If you think about it, do we really need to know the exact time of the event or the data? So for example, let's say for this, okay, let's say for this message, it shows the time is 9:31. Does it really matter it is 9:31 or 9:35? As long as it's not that far away, as long as it's not 10:35, right? So I think it's okay if it's 9:35 or 9:31. Either time is okay because they are close to each other, right? It doesn't matter. What it really matters is the relative order of the time, right? So for example, let's say this comment, you own Model X, let's drag it down, okay? So because the second comment happens after the first comment, especially it's because of the first comment, then there's a second comment, right? So the time here, this time should be after the first time, okay? So this should be sometime after 31, right? So it can be 34, okay? So what really matters is the relative order of the time, right? So it's not the time itself, right? So for example, this time it could also be 9:35, right? And as long as the second comment time is after that, let's say it's 9:38, then it's fine, right? I don't care about the time itself. What we really care about is order of the time, right? Or the order of the events. That's what we care. So this gives a solution, and it's one of the typical solutions is vector clock. So now let's see what is vector clock and how we use it. Okay, cool. Okay, now let's copy this. See, vector clock to solve time differences between different machines in distributed systems. Okay, cool. So now let's say, okay, so let's say we have two machines, okay, for data replication. Okay, so if you don't remember what is data replication and how to guarantee strong consistency in data replications, you can go back to my previous video, which specifically talks about data replication in very details, right? So I pasted the link in the description of this video, and you can always check that video first and then come back to this video. Okay, cool. So we have two machines. Okay, so let's say when I write a data, the data will be write to both of the machines, so the data is replicated, so we can have a high availability system. Okay, and with vector clock, each machine in the replication, they will have a counter. So let's say this is a machine A, its current counter is 0, okay? And this is machine B, its counter is also initialized as 0. Vector clock means each machine has a copy of the other machine's counter as an array. So for example, so this machine A, its vector clock will look like this. So basically it's an array. It will like this. So A's counter, which is itself's counter, is 0. And B's counter is also 0. Okay? And same for machine B. So my vector clock is A is 0, B is 0. Okay? So this array, which has the counters of all the machines, this array itself is called vector clock. So each machine in the replication, they will have, all of them will have vector clocks. Okay, cool. And if you remember what we talked previously, okay, in order to guarantee strong consistency, R plus W need to be larger than N. So R means when you read the data, how many machines you need to get response from. W means in order to write a data, how many responses from how many machines you should have in order to consider the write is successful, right? And N is the replication factor, which means how many machines do you have in the replication. So in our case, let's say W equals to 1, which means as long as the data is written to one machine, then we consider the write is successful, right? And then the replication from the machine A to machine B happens after the write is committed, okay? And because in this case, N equals 2, because we have two machines in the replication, right? And then based on this rule, right, R plus W must be larger than N, then we say R must be 2, right? Which means when a read comes, we must read the data from both machines, okay? And we compare the data from these two machines and then respond back to the client, right? So we must have the read response from the two machines. This is what R equals 2 means, okay? So now let's say A is the leader machine, right, in the replication, which means all write will go to A first, okay? So now let's say for a data X, okay, we write the data X to A, okay? So data X equals to 2, okay? And when A writes the data, okay, it will increase its clock. So it will increase to 1. Also for X, so along with the data X, we will also store the vector clock together with this X, okay? So for this X, we know the vector clock is A equals to 1 because we increased A to 1, right? And B is still 0, okay? Cool. And now then the write respond back to the client and it says the write is successful, okay? And then the data will be replicated from machine A to machine B, right? And when it replicates to machine B first, it will increase its counter to 1, okay? Because receive a replication message is also an event, right? So whenever you have an event, you must increase the counter, okay? So B's counter becomes 1, okay? And now for data X, when X is written to server B, it also stores the vector clock together with the data itself, right? So in this case, when A sends the data, replicates the data X to machine B, it also sends its clock to machine B, okay? Okay, so let's remove this first, okay? So the data received by machine B during replication is, X equals to 2, and also the vector clock from machine A, right? And now machine B will check its own counter with the counter from this vector clock. I found my counter 1 is larger than this vector clock, which is 0, right? So then I will update this vector clock to the maximum of the both numbers. So this b will become 1. Okay, and then I store x2 and also the vector clock in the database. And then next time, maybe a new write comes. Okay, so let's say now I changed x to 5. Okay, similarly, the request will hit the leader machine, which is A first, right? So then data A will first, because this is a new event, right? So A increases counter by 2. Okay, now the X will be written to database. Okay, and also with the latest counter. Okay, so the latest counter from A is 2. So this is what's stored in database. Okay, and the write respond back to client. It says, yeah, write is successful. And similarly, this data during replication, it will be sent to client B. Okay, and client B receives this replication event, right? So it also updates its counter to 2, which is increased by 1, right? And also he saw, oh, in the vector clock sent by A, okay, my clock is still 0, right? But my current clock is already 2, which is larger than the 0. So now I update it to 2, okay? And then I store the latest data in the database. So the old data is removed. Now this is the latest data. Okay, cool. So this is how vector clocks work. Okay, so now let's say something happened, which is this leader machine. Okay, this leader machine goes down. So it's dead. Okay. So this leader machine dies. Okay. Now we only have one machine left, which is machine B. Okay. So because our factor, so machine B currently will be elected as a new leader, right? Because he's the only left machine, right? So because our write factor is 1, which means as long as we have one machine, then we can continue the write, right? So in this case, even machine A is done and we only have one machine left, we can still continue to receive new writes, right? Now let's say we have a new write which says x equals to, let's say 8. Okay, so machine B receives this write request. So because it's a new event, machine B will increase its counter, which is 3. Okay, so and also I will store this data, right? And currently for data X, the clock is A2, B2, right? So now I will update it to, because B is already 3 now, so I update the vector clock for data X to 3. And also store the new data in the database, which is 8. Okay, cool. So this is what it looks like, right? And now let's consider there is also another write, which is x equals to 1. Okay, so we also update the counter of B to 4, and also the vector clock for data X will also be updated to 4. Okay, and the data will be updated to 1. Okay, cool. Now things goes on, and somehow machine B comes, machine A comes back. Okay, cool. Machine A comes back, and then machine A becomes the leader again, let's say. Okay, cool. And now we want to read the data. Okay, so machine A recovers. Now let's say I have a read request comes, which is, what is X value? Okay, a read request comes. Because the factor for read is 2, which means we must read data from both machines, right? So we read data from A. We also read data from B, okay? And the data we get from A is X equals to 5. And also the data read from B is X equals to 1. So there is a conflict here, right? So because machine A says a different data than machine B. Okay, cool. So now what happens? Then we compare the vector clock. So we can see which one is latest data, right? So if you compare the vector clock, so for this array, you can see for A from machine, the vector from machine A, so the value for A is 2. And the value for A is also 2 on machine B. Okay, so they are equal, right? But for B on machine A, it says it's 0. And for machine B, it says the counter for B is 4. So basically, all the numbers in the vector clock from machine A is less or equal than all the array numbers from machine B, which means the data from machine B is the latest data. Okay, so then we return X is actually 1. Okay, and it returns it. Okay, cool. And because we know there is some discrepancy of the data between the machines, right? So after the read, you can do a further optimization, which is you also write the latest data X back to the machine A, right? And then the vector clock between the two machines will be the same. Okay, so this is the first case, right? So we know based on vector clock, we know which data is latest on which machine, and we can resolve the conflict, right? So now let's see a different use case, which is we cannot resolve the conflict actually. Okay, cool. Now let's go back to the previous status in the example. Okay, so let's say it's 5. Let's see, it's 5 and the counter is 2. Okay, so this is a previous status. Okay, so this is the vector clock on the machine A, this is vector clock on machine B. Because nothing weird happens, the data on both machines are exactly the same, right? And this is vector clock from machine A, and this is vector clock from machine B for data X. Okay, cool. Now let's say it's not machine A who dies. Okay, it's what happens is there is a network partition. Okay, cool. So there's a network. What network partition means? So machine A is disconnected from machine B. They don't know each other's existence, right? Even though both of them are actually alive. Okay, because somehow the network is disconnected or unstable between these two machines. Okay, which could happen very frequently in real case actually. And now let's say some clients, okay, they are still connected to machine A, and some clients, they can still see machine B. Okay, so for these clients who are connected to machine A, because okay, they know there is only one machine left, which is machine A, right? And because as long as we have one machine, we can continue the write. So for these clients, okay, let's draw it out. Okay. So here we still have some clients connected to this machine A, and also we have some clients connected to machine B. Okay, cool. Okay, so for these clients, because they can only see machine A, and we know as long as we have one machine left, we can continue the write, right? So these clients can still write the data to machine A. Okay, and for these clients, they can only see machine B now. And as long as we only have one machine left, we can continue the write, right? So for these clients, machine B is the leader now, and they can write the data to machine B, right? So now let's say from client who connects to machine A, okay, now there is a new write, which is I want to update X to number 12. Okay, so similarly, so for machine A, I increase my counter, which is 3, and I wrote the latest data to 12 to the data list. But also along with the data, I will also update the vector clock to the latest counter, which is 3 now, right? And then I respond back to the client to say, oh, the write is succeed now, right? And similarly, maybe I can have some further writes, which I updated the counter to 4 and the data becomes 15. And also here it becomes 4. Okay, cool. And on the other hand, for machine B, it also continues to receive new writes from these clients who can only see machine B, right? Now let's see some clients write a new data which says, oh, x equals to, let's see, 90, okay? So we update our counter by increasing it by 1, which becomes 3 now, right? So we write the data here, and also we update the counter for B here to 3. Okay, cool. And now let's see a new write which updates it to, let's say, 20. Okay, and then I updated the counter to 4. I updated the counter to 4 in this vector clock for x. Okay, and it becomes 20 now. Cool. And then the write respond back to the client. Okay, so this is the current status. Okay, now let's see the network partition goes away, which means the system resumes to a normal status. So we can see both machines now, and A is still the leader. Okay, now what happens if a read comes? Okay, so now I want to read data X. Data X, okay. So because our read factor is 2, which means we must read data from 2 machines to consider a successful read, right? So here we read data from A, we read data from B, okay? And now the data from A is 15, the data from B is 20, okay? And as we mentioned previously, we need to, this is conflict, right? So we need to resolve the conflict by comparing the vector clock, okay? So let's compare the vector clock. So on machine A, the counter for machine A says 4. And on machine B, the counter for machine A says 2, right? Because 4 is larger than 2, it says the data on machine A should be the latest one, right? But if we continue to compare the counter in the array, which is B, the counter for B now, right? So we can see on machine B, the counter for B is 4, while on machine A it's 0. So based on this B counter, okay, now it says a different result, which says, oh, machine B's data is actually the latest data, right? Because 4 is larger than 0. Okay, so now, so based on counter from A, it says, machine A has the latest data. And based on counter on B, it says machine B has the latest data. So we cannot resolve the conflict, right? In this case, we actually have several mechanisms to resolve the conflict. First mechanism is you can just return both data to the client, right? And then client can, based on their business logic or any other assumptions, they can just say, okay, I want to take X to 15 as the latest data. And when clients finish the read, it also writes back the data to both DB, okay, which overrides all data to 15, okay? Or the clients could say, oh, I want to take X as 20 as the latest data, and he writes back 20 as the latest data to both machines. So this conflict will be resolved by client, okay? Another mechanism we can take is we just resolve the conflict internally. So basically, we just randomly select either of them. So let's say we select the larger number, which is 20 as the latest data. So we return 20 to the client, okay? And then we write this data back to machine A. And machine A now we will have the latest data. So this is how we resolve conflict, okay? Cool. So now you can see how we use vector clock to determine which data is the latest on the machine. And if there is conflict we cannot resolve, how we can resolve the conflict, right? Okay, cool. So this is all about this video, where we introduced the time in distributed systems and how we can use logical times, which is vector clock, to solve the time difference problems among different machines. Okay, so if you like this video, please give a thumb up and give me a like, and also subscribe to this channel. Thanks for your support in advance. Thank you. Bye bye. See you next time.